Today we want to finish up the last parts of trigonometric substitution before we have to start practicing trigonometric substitution problems. Remember that our plan is to go from an x integral. So we start with an x integral and we see some quadratic nonsense going on in our x integral. And so it makes us think, let's do a trigonometric substitution, trade our x integral for a theta integral, and then integrate the theta integral. Then we learned how to undo the trig substitution to go from our theta antiderivative to back to our x antiderivative. So the opening and the end game for trigonometric substitution tend to always work the same way. The opening is decide the case, make your substitution, two terms become one. We're at the theta integral. The end game is also always the same. Take your original substitution, solve for the trig function, solve for theta, and then do the triangle thing to get your x antiderivative. The weirdness happens in the integrate step. We're usually looking at products of powers of trig functions in our theta integral that are not substitution. If the theta integral is substitution, your x integral was substitution. Go back and do the substitution there. Otherwise, you're just integrating with lots of extra steps. So to that end, we needed to figure out which products of powers of trig functions were not substitutions. And that was even powers of cosine or sine, or odd powers of secant without tangents. Those are the two cases of products of powers of trig functions that are not substitutions. Notice that odd powers of secant without tangents includes odd powers of secants with even tangents. But we're going to rewrite our expressions as odd powers of secants without tangents. So odd powers of secants without tangents. Similarly to cosine, even powers of cosine, including even powers of sine. Odd powers of secant without tangents. This includes but the case we're going to reduce that to is odd powers of secants without tangents. Since odd powers of secants without tangents for powers greater than 1 just boils down to doing parts, you can also do parts with the even powers of tangents there. But just like I said, I want to summarize the even powers of cosine. I'm just going to call it even powers of cosine, even though that includes sine. So if we have even powers of cosines and sines, everything is still getting converted to cosine of 2x. Whether you go the way that I think about it, which is to convert the sines to cosines, and then just use cosine squared as a half plus a half cosine of 2x, or whether you choose to solve for sine squared and replace the sine squared with its other expression in cosine. All right. So when we're looking at odd powers of secants without tangents, the first one we need to deal with is one that we technically already know. So last time I said, here's our first one. This is the first odd power of secant without tangent. Integral of secant to the first. The integral of secant is the natural log of the absolute value of secant x plus tangent x plus some constant. I mean, obviously, right? That's exactly what you would have guessed. Or maybe not. So we got to think about one thing we can do is just stop right here. You can say, I'm just an engineer. I don't care where it came from. I know this works. I'm done. I don't need to understand what's going on. That's very practical. You're thinking of yourself as having a limited capacity for storage. And it's like, oh, knowing where this came from, that seems like storage I don't need. If someone asks me for the integral of secant x dx, I know it's natural log of the absolute value of secant x plus tangent x plus some constant of integration. And if everybody says, where'd you get that from? You're gonna say, take the derivative and see how it works. Then it says, oh, but how'd you know that this is the derivative of this function would give you secant? You'd be like, oh, quiet, you. So you could just justify this with because I said so. Notice that the derivative of natural log of secant x plus tangent x is going to be 1 over secant x plus tangent x times the derivative of secant x plus tangent x. So to think about where we would get this integral, think about the derivative of the natural log of the absolute value of secant x plus tangent x. So the derivative of natural log of something is 1 over that thing times the derivative of that thing. The derivative of secant x is secant x tangent x. The derivative of tangent x is secant squared. If we want to see what this expression is made of, notice that in the numerator, I have a common factor of secant. And if I factor that out, I'm left with tangent x plus secant x. And tangent x plus secant x then cancels out with the secant x plus tangent x in the denominator. So we took the derivative of natural log of the absolute value of secant x plus tangent x, and we get secant x. The main thing that happened is that the secant x plus tangent x canceled out. So that tells us how to integrate secant x. Keep in mind, this is telling us how to integrate secant x when we already knew what the answer was. I'm not saying that this is the creative way where we take secant x, know nothing, and then come up with the natural log. But this is an important discovery. Noticing that the derivative of the natural log of secant x plus tangent x is secant x. And the main thing that happened here after we took the derivative is that we canceled out secant x plus tangent x. That's the important part. So when we go to set up an integral for secant x, so if we want to calculate the integral of secant x dx, the first step in the integral is the last step when we took the derivative. In the derivative, we canceled out secant x plus tangent x over secant x plus tangent x. So if we're integrating, we need to put that back. So I'm going to take secant x, and I'm going to multiply by 1. One of the great tricks of math, multiply by 1. Like getting a common denominator or converting some units. Multiply by 1. So our integral will be the integral of, on the top, secant squared plus secant tangent. And in the denominator, secant x plus tangent x. If we think back to the previous page, the way we took the derivative of the natural log of the absolute value was to do 1 over and then multiply by the derivative of the thing. 1 over the thing times the derivative of the thing. That is, we are using the chain rule. So now that we're doing integration and going backwards, we're going to do the anti-chain rule. We're going to do substitution. And since we know the answer is going to be a natural log, our substitution is going to be the denominator. So if I make W secant x plus tangent x, then dW is secant x tangent x plus secant squared dx. So our integral is just going to be one over W dW. I don't think it's critical to know how to integrate the secant x into the natural log of secant x plus tangent x. I don't think that's critical. If my movie is running too long, then that's the scene that ends up on the cutting room floor. We don't really lose anything by doing that. We can just remember integral of secant x is natural log of the absolute value of secant x plus tangent x. But in case we start wondering, let's take the opportunity to reinforce the connection between integration and differentiation, where we're thinking about integration as inverse, or integration and differentiation as inverse processes. So if we think of the order of go in the derivative, we did the chain rule, then we canceled out. So if we're undoing that, we undo the cancel by multiplying by 1, putting the stuff back. We undo the chain rule by doing integration by substitution. Just like when we're solving equations. Any questions? Even though when you might not have been in my algebra class where I emphasize solving equations by doing inverse operations in reverse order. So earlier, when I'm like all inverse operations in reverse order, that was supposed to have more impact, but you haven't seen the previous movie, so you're like, oh, what? It's kind of like in Star Trek Into Darkness, when Benedict Cumberbatch shows up and has the big reveal where he's like, oh, I'm Khan. No one gives a shit in that universe. He does not have the same, it's not the same. It's not the same. There's no history in the new Star Trek movies between Kirk and Khan. So when Benedict Cumberbatch shows up, he's like, "Oh, I'm a badass," like Khan is supposed to be. No one should actually care. If all you've seen is the new Star Trek movies, that is meaningless, which means these movies shouldn't have been made. That's just me. Especially if you're being so transparent and you're like, "Oh, no, 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 no. The villain isn't Khan." If you like just directly lying to your audience, then just no. You're missing the point. You know what I mean? It's like we're just supposed to assume that Kirk and Spock are friends now. And the way they had to demonstrate that is they told us at the beginning of the movie, "Hey, Kirk and Spock are friends now." It didn't happen on screen where we watched it over however many episodes of original Star Trek, however many Star Trek movies, where Kirk and Spock became friends. They showed us them becoming friends. They had to just tell us that they're friends now and rely on the audience's history knowing that Kirk and Spock are friends. You know what I mean? You essentially become the DM doing a lore dump. Your players probably don't want that. At a table of 5 players, every other group will have one player that's just sitting there writing down every piece of lore and is trying to fill in the history. But anyway, what are we talking about? So this was accomplished using my favorite inverse operations in reverse order. Just start undoing stuff. Y'all don't have a history with inverse operations in reverse order because y'all just met me. And so I'm like, "Oh, Khan," but it's like, "Oh, who the hell is that?" Okay. So if we have, this is going to be important because this is going to be one of our building blocks. The rest is going to be pretty straightforward. Next up is why I just say even or odd powers of secant without tangents and include odd powers of secants paired with even powers of tangents. The main reason I want to consider this as odd powers of secant is that first of all, I can convert my tangents into secants when they show up in pairs. The reason I would want to do that is to build an iterative process. Because I'm worried about sine to the first, sine to the third, sine to the fifth. If I can write sine to the third in terms of sine to the first, or sorry, secant to the third in terms of the integral of secant to the first, and then use that to generalize. So I can write this, the integral of secant to the fifth in terms of integral of secant to the third and secant to the first, then it's better to think about just odd powers of secant and make the tangents go away. That way we're not just reintegrating the problem every single time. So I'm going to read tangent squared as secant squared plus 1. Oh, minus 1. And see this as the integral of secant cubed x minus integral of, oh, I didn't separate that, minus secant x. The x. So I'm thinking of 2 integrals, the integral of secant cubed x dx, the new one, and the one that we already know. So I want to see what's going on from secant x to secant cube. What changes from secant cube to secant to the fifth? Let's find a pattern so that we can integrate secant to the 11th when it comes out. I shouldn't say when secant to the 11th comes out. I should say if secant to the 11th comes out. That way I don't reveal that on the final exam. It's just integrate secant to the 11th. I'm just kidding. That's a joke that doesn't have a lot of impact because you haven't seen how bad this process can be. Bad? I don't know. Annoying? Yes, definitely. So here's what we want to do. We want to focus on these new integrals. So let's just focus on integral of secant cubed x dx. We know that this is not substitution. That's why we're looking at this and spending too much time on it. We know it's not substitution. Our other option is to try parts. So let's think in terms of parts. Now, in this case, u is something that we differentiate. dv is something we can integrate. There are a bunch of ways that we can deploy. We can go secant cubed and 1, secant squared and secant and secant squared, or 1 and secant cubed. But that last one doesn't make any sense at all, because if I could integrate secant cubed of x in the dv slots, then I would just do that. So that last one. So really only got 3 choices. The rule is that dv has to be something that you can integrate. I can integrate 1 into an x. I don't really like the idea of mixing x's and a bunch of secants and tangents. That seems like it's going to make things worse. I could integrate secant squared for u, or I could have secant squared for u and 1 secant for the dv. I don't really like that plan either, because the integral of secant x is the natural log of the absolute value of secant x plus tangent x. And that sounds like it's going to make things worse. So what might make things better is to put in the dv slot secant squared, because the integral of secant squared is tangent. And then I'm just going to have some combination of tangents and secants. So that's pretty good. So I'm going to dv has to be something I can integrate. I can integrate secant squared x. That leaves for you secant x. Now I find du by differentiating. It's going to give me secant x tangent x dx. And the dv will tell us that v is equal to tangent x. That seems to me to be the most appealing of our 3 options. So the integral of u dv is uv, so secant x tangent x. Minus the integral of v times du. And that's going to be tangent times secant x tangent x. So secant x tangent squared x. So we're once again in the odd powers of secant category. I have secant and tangent squared. So now we can see why I did that one where I replaced the tangent squared and didn't just talk my way through it. Because now I'm going to replace the tangent squared with the secant squared minus 1. And this integral of secant tangent squared is going to end up being an integral of secant cubed minus an integral of secant. This is significant because the integral of secant cubed is the one that we're looking for. So we're going to do that parts thing where we move the one that we're looking for onto the other side and just have 2 copies of secant cubed. So this side of the equation is looking like secant x tangent x minus a secant cubed x to x plus a secant x, an integral of secant x dx. Chekhov's integral. Now, the reason that this is important is that the integral that we're looking for is this secant cubed x. And a copy of it has just shown up on the other side of this equation. So I'm going to say, if I just add a copy of secant cubed x, two integrals of secant cubed is a secant tangent. I move this one away, and the integral of secant x is a natural log of the absolute value of secant x plus tangent x. And then we can just divide everything by 2. So this involves a lot of our part stuff. So by doing trigonometric substitution and going this far, we get to reinforce some of the things that we saw in parts. It's like most of your trig class is there to reinforce your algebra skills as you're moving on. Like all those trig identities, that wasn't about trigonometry where you had to prove the identity, where you had some wacky identity that's not listed in any list of identities anywhere, because it's not really useful, except as an algebra exercise. Those prove the trig identity problems were not about remembering your trig identities. They were about reinforcing your algebra skills. And so here we have an opportunity to reinforce our parts skills, in particular, the one where the integral we're looking for shows up on the right side. I don't know what movie trope that would fall into. The answer has been there right along. You've had the ability to go home all along. Or the villain was the person you least expected. Any questions? The next thing you want to do is to go integrate secant to the 5th. So think about what you could do with secant to the 5th and go attempt that. A lot of this, expect a lot of the same things to happen with the secant to the cube, secant cube. And then try to integrate the secant to the 5th. That would be a useful exercise. Not an important piece of information to know, but it would be good training. All right, that's going to do it for today. I'll see y'all on tomorrow. But have a good day and thanks for playing.